Welcome everyone, and this is IEEE SecDev 2020 tutorial on principles and practices of cryptographic coding in Java. So this is a joint tutorial given by my PhD students, Miles, Sharmin, and Professor Sazzadur Rahaman from University of Arizona. And I'd like to acknowledge NSF funding as well as ONR, Office of Naval Research, for supporting our project. Our collaborators also include Bart Miller from UW-Madison, Namon from Virginia Tech, and Christina Cifuentes at Oracle Lab, Australia. Software is everywhere, and this is something that we're so familiar with, but I just want to emphasize a little bit more. Recently, a newer model of Ford pickup truck, F-150, has 100 million lines of code. And part of the reason is because it has many sensors, electronic control unit. Each of those devices has code, and so it's really add up. In comparison, some of the more important devices, like aviation devices, the Boeing 787, F-22 Raptors, have way fewer lines of code. And in aviation industry, is a longer industry has a longer tradition of regulation on code writing, verification, and vehicle smart cars is just does not have that much regulation. And so you just wonder how many vulnerabilities are there. Similarly, if you look at this is the 2017 data from an international group that look at a lot of the industry control systems, vulnerabilities reported, and many of them, cross-site request forgery, cross-site scripting, are just like ordinary vulnerabilities on workstations, on web servers. And so this type of a software vulnerability is permeating through all parts of our life. In 2016, this is the day right before Black Friday, the Thanksgiving day, San Francisco Municipal Transportation Agent was hacked and subject to a ransomware attack. The hackers demand 100 Bitcoins, which at that time is almost $1 million. Right now, this is September the 1st. I checked, 1 Bitcoin is about $12,000. And so you cannot get ticket, and so San Francisco Transportation Agency decided to have free subway rides on the Black Friday, this shopping day. And so interestingly, they didn't have to pay because turns out that all the devices got hacked were dumb terminals. It didn't store any sensitive information. All the data centers are kept intact. But a lot of people are not that lucky. This is a statistic that shows that only half of the people who paid the ransom get their data back. But 19.6% of them lost their data. And luckily, a lot of people who have backups and preparation ahead of time, so they didn't have to pay the ransom. The software vulnerabilities are just getting closer and closer to your body, wearable devices, medical devices, and they will have, if compromised, if having vulnerability issues, will have a much bigger impact on people's health. And so it's needless to say those issues are important. And for years and years, the developer has been going through principles, lessons, trainings to educate developers what to do, the secure coding strategies. And we also need tools. We need tools to support them. And we need both education and the writing tools. And the community need to support developers. But the tools, how good are the tools? And how well are the tools designed for deployment? And those are something that our group has been studying for a while. And through this tutorial, we hope to deliver the message that it's important. The community also need to do more. And this is the Microsoft, very well-known Microsoft secure development lifecycle. And so this is sort of a guideline for developing the development time and design time, secure code writing, and involving a lot of tool verification back and forth. And so developers definitely need tools, and there are tools. But then, however, we still see vulnerabilities, and sometimes people blame on developers, but who would not want to write secure code? Time, budget, resource, lack of resources, and sometimes the tools generate too many false positives, and those are all issues that make it harder and harder, and then it just build up, so that some developers just give up. They search Stackoverflow to find the quick and dirty fix. And so the more I look at this problem, the more I see the gap between security theory, and you can say it's a cryptographic theory, program analysis theory, to deployment. And so there's a big gap. On many of the issues, for example, cross-site request forgery, this is very well known. 2008, there was a highly cited paper that reported this vulnerability for web browsers. Highly cited, but until now, how well is this solved, right? So are we eliminating, like 12 years later, are we eliminating all CSRF vulnerabilities? So just very quickly, what is CFRF? The problem is where the browser may automatically attach a victim, a user's credential, to send to a server on a request that's not intended by the victim. And so the victim may be tricked into clicking a link, a button, visiting a website, and end up triggering a submission of form. And that form could be used for password changing, bank fund transfer. And then the browser didn't know that this is a malicious request and end up automatically attach the credential. So this is also called confused deputy problem. It's one type of confused deputy problem. And however, people need help, developer need help. And this is a real quote from Stackoverflow. Spring Security, Java Spring Framework actually has support for CSRF prevention, and then a lot of people don't know how to use it and end up disabling it. And people say, I have no idea why it was enabled by default. And so sometimes it's hard, because if you graduate school before CSRF vulnerability was discovered, and then you never sort of got an official chance to learn about this. And here in the 2018 study with my colleague Rahaman at Virginia Tech, we look at a lot of the Stack Overflow posts, and here are some quotes. And what I really like is this one: I want my client to accept any certificate because I'm the only server that they're gonna point to. I suspect this is the app writer, app developer, and so they were like, okay, if I write the app so that when it's fired up, it would directly contact to my server. Conceptually, it makes sense, you know, the statement makes sense, but however, there are so many complications. What if the app get hacked? You know, what if the you know, get intercepted, the traffic get intercepted? You will have to verify certificate, right? And so we look at that. In that same study, we look at 17 problematic posts on Stack Overflow, and we find out they are extremely influential, and you can call it influencers, social influencers. They were viewed by that time, as of August 2017, viewed 600,000 times, and so extremely influential. Those vulnerabilities and teaching people to do, you know, trust all certificates and so on. And then interestingly, we also find some sort of cyberbullying going on Stack Overflow. This is actually real quotes. Some new user has no reputation, and this is sort of the reputation score on Stack Overflow based on how many answers you respond to and how many accepted answers and so on. And this person got scolded by a more experienced user. Just say, oh, you don't know much because you haven't answered, you haven't really answered anything. But this junior people actually encourage people to write more secure code. Paparazzi doesn't help. After our paper published, there is an article reporting our work, but then it's put words in our mouths, and we never said lazy developers, and it's really not developers' fault. The problem is just complicated. And so part of this tutorial, we want to talk about the problems, the crypto API, the TLS, and then leads to some of the tools that developer may consider using. And this is the we have worked on CryptoGuard for a long time. Sazzadur, who recently joined the University of Arizona, came from our group. He's a lead designer of CryptoGuard, and then the work was also, our approach was also adopted by Oracle Labs to screen their internal production code. And so one of our main effort was spent on reducing false positives, increased precision. We also put together a benchmark and did a lot of work. And there's a very easy to read article explaining CryptoGuard and then the context behind it. And a little bit of overview of what's coming up today. We want to do a couple of coding exercise, and I know it's extremely sort of frustrating to read code, and so we hopefully make it easier and for you. But then you don't have to memorize the code, obviously. But we just want to point out the issues. The issue may show when you write crypto code using crypto APIs in Java, and when you use TLS, write TLS code. And we hope that you remember some of the strategies. And we want to give an introduction to our tool. And of course, this is developing. We're still working on it to make it better, to improve it. We are very proud that we put together a benchmark, which hopefully will drive the field to improve all of us to continue working, improve the accuracy, performance, and so on. The take-home message, I think I really hope at the end of the tutorial that you remember that there are actually tools, strategies, and a lot of resources to help developers to write secure code. Developers are not alone, and also, they need help, and we hear their cries and for help, and so the community, I think, is also working very hard to enable developers and everyone to write better code. So that's the introduction, and then this is a summary of some of the references. And the next one coming up is Sharmin Afrose, who is a third year PhD student in my group. And she's going to go through some exercise to see whether you can tell secure code from insecure code.
Okay, so I'm going to show very simple secure versus insecure code examples. So I will start with very easy first, and then it will go like 2 or 3 lines of course you will see in this part. So let's see for code examples for URL. So in this 2 code snippet, you can see that there is 2 URLs here. So one URL start with HTTP and another URL start with HTTPS. So which one do you think secure or insecure? So I think you already guessed that HTTP is insecure because HTTP lacks encryption. For the secure part, HTTPS is actually HTTP with encryption. So the user's data will be secured if you use HTTPS. So in the next example, we will see the random numbers generation. So in this side, the random API is used, and in this side, the secure random API is used. As you can guess, seeing this secure prefix, that this one is secure and this one is insecure. So the random number generated using this random API actually takes a definite mathematical algorithm, so which makes it predictable. For the secure random, this actually creates the random number which is unpredictable and non-deterministic. Okay, so let's see the next example. So the message digest API, it actually takes an algorithm, a hash algorithm. So in this case, in this code snippet, it takes MD5, and in this code snippet, it takes SHA-256. So which algorithm uses is secure and which is insecure? So I think you have already guessed that MD5 is insecure because MD5 is now vulnerable as it has the collision. It is vulnerable to collision attack, and for this SHA-256 is actually a strong secure hash algorithm. Okay, so next let's see the ciphers for encryption and decryption. This actually created using DS algorithm, ECB, and this is actually takes the AES and CBC. So what is so which one is secure and which one is insecure? So we can see that DE is actually insecure because DE is actually broken. It is considered broken as adversaries. They can do brute force attack for 64-bit ciphers, and ECB is actually it can actually shows what is inside the plain text in abstract way. And for the AES, it's actually extend this is actually extended version of has extended key value and extended block size. So this is more secure than DES. And the cipher block chaining, this is more secure than ECB. This is the generation for the cryptographic keys. Secret key aspect do is that it actually generates a secret key using a byte array. So this key byte and this key byte, they actually generate in a different way in these 2 code snippet. So which one do you think secure and which one is insecure? So we see that in this case, the SecDev 2020, this is a constant string, and this string is used to produce these key bytes. So this is a constant value, and any attacker can intercept this string, can guess what the secret key is, and then the purpose of encryption will be invalid. And for secure case, we can see that random, unpredictable, and non-deterministic key bytes is always getting generated. So in this case, this is more secure, as attackers cannot guess what the key bytes would be. So these are the simple examples we have now shown, and after this, Xiao will present some more secure versus insecure examples.
Hello, the next part, I will introduce some JSSE code examples for the TLS and SSL authentication. Many studies have pointed out that TLS and SSL are pretty important. Misconfiguration of it can cause the man-in-the-middle attacks. Here is a piece of code to build a HTTPS connection protected by the TLS. At the line 3, when we get the input string, all the TLS authentication happens implicitly like that. And if any exception occurs and throughout, the connection will be terminated. However, not all the exceptions occurs because of the attackers. Sometimes even the legitimate users could also raise the exceptions due to the configuration issues. And to fix this kind of exceptions, we need to securely customize the trust manager and the hostname verifier. Trust manager and hostname verifier are two JSSE interfaces taking control of the authentication process. And their working logic is shown here. The trust manager is responsible to verify whether the certificate is legitimate, and then the hostname verifier is responsible to verify whether the hostname appearing in the URL matches to the names appearing in the certificate. And therefore, we need to customize them carefully and to avoid any security vulnerabilities. And next we'll walk through several examples. Next we'll walk through several examples of the customized trust managers to see whether they are secure or not. This is the example 1. This is a class implementing the trust manager. And there are two methods at line 3 and line 8. They define the verification logic for the certificate we received. So whether this is a secure example, we can see here it is not secure because actually no verification happens here. And the empty method body just means doing nothing, and any certificate could bypass this pass this process. And this is the second example. You may notice that at line 8, the verification behavior happens. However, whether this is a secure example, the answer is still no, because actually we expect the unlegitimate certificate could raise exceptions to terminate the communication. However, at line 10, all the exceptions are kept, and in this way, in this way, any exceptions is caught without handling. So any certificate could pass the verification. And this is another example which is more complicated. At line 10, the verification behavior happens and without catching the exception. So do you think it is a secure example? And the answer is still no, because it only performs the verification under some conditions. And when the certificate chain, the length equals to 1, that indicates that we only receive a single certificate rather than a chain with the intermediate certificate attached. In this case, it will only did the check validity rather than the verification behavior. And the method check validity, it only checks whether this certificate is expired, and it cannot tell about whether it is a legitimate one. So in that case, the attacker is easy to bypass the authentication by only sending a single certificate without a complete chain. And next, we will show you several secure ways to customize the trust manager. And the full examples is shown in this GitHub. We only display some key parts here. First, we describe a scenario. That is, maybe you are developing a client, and this client wants to visit an internal server, which only has a self-signed certificate. Another situation could be like your code is under the development mode, and the server has not got the official certificate yet. So the secure way to do it is through the key store. And the key store is a Java entity to store all the certificate we trust, including the intermediate CA certificates. And the recommended practice is that if you want to trust this certificate, you just put it in the key store, and the trust manager relies on the key store to make decisions. Here is the code doing so, and we do not expect you to memorize every line of the code, just get to know the concept. And the take-home message is that always configure your key store rather than disabling the verification logic. Here we can see that the special trust.crt is the file of the certificate, and it is loaded into a trust manager we created here. And this trust manager is fit into this key store is fit into a trust manager, and using this trust manager, we can let the certificates we trust to pass the verification. And then we describe another scenario, like your clients want to both visit the internal server and also some external servers as normal. And in that case, you may need 2 key stores. And one is the key store you specified. And the second is a default key store locating in that directory in your system. And you may need 2 trust managers to trust them separately. Another choice could be you could mix these certificates into 1 key store, but it is not recommended because for the management purpose, because sometimes people want to manage some a key store separately for the system, and also maybe different key stores for different applications. So next, we show you how to use 2 key stores together. And this is a customized trust manager. It actually includes 2 separate trust managers. One is called default TM, and the other called backup TM. And the default TM, we just use the system key store, and the backup TM, we just relies on the specified key store as we introduced in the example 1. So this time we need to override this method this check server trusted, which specifies the verification logic. And here at line 11, we first use the default trust manager to verify the certificate. And if any exception occurs, we will call the backup TM to see whether it can be handled by this trust manager. Another situation is similar, just like if you have more than 2 key stores. And the example is like that. You just need the trust manager, and it includes a list of trust managers, and each one may be released on different key stores. And the verification logic is like at the line 10. You use them in order, and if the certificate is trusted by any of the trust manager, this process is returned normally. And if none of them could recognize this certificate, it will raise an exception to terminate the connection. And next, we move on the hostname verifier part. The hostname verifier is responsible to match the hostname to the name appearing in the certificate. But sometimes, due to many reasons, maybe the virtual hosting, like the certificate may have lots of names, a common name and some alternative name, or maybe a server has multiple certificates. So maybe it returns a wrong name like that. So in that case, we need to customize the hostname verifier, and this is an example. Let's to see whether it is a secure example. And we can easily figure out that it is not secure because no matter the host name is, it will return true. Always let it pass the verification. And this is another example. We can see at line 12, the URL, actually the hostname appearing in the URL ends with .org. However, the name we expect in the certificates ends with .com. So to fix this issue, to handle it, it uses a customized hostname verifier and to specify the expected hostname here. So this is actually a secure example. And this hostname verifier only uses for this connection. And finally, we talk about another vulnerability type happening when we using the SSL socket factory. Previously, we showed the code snippets to build an HTTPS connection. However, the TLS could also support other protocols. So sometimes we need to use some low-level APIs like the SSL socket factory to build the connection. And an issue we need to notice is that when we build the connection with the SSL socket factory, the implicit authentication only includes the first step we introduced, which is handled by the trust manager. And the second step, which is handled by the hostname verifier, is missing. So we have to manually do that to guarantee the security. And next, I will show you some examples to make it more clear. This is the example 1. There is a socket, and this socket is built from the SSL socket factory. And when we use these sockets, all the implicit authentication, or we should say that incomplete authentication happens. And this is an insecure example because the authentication only includes the trust manager without the hostname verification. So this is an example, like how can we secure this connection? And from the line 5, we need to insert an extra part to manually obtain a hostname verifier and manually do the verification. If the return value is false, we need to throw an exception for it. And this is another example also could use to secure the connection. It's doing it in another way, that is setting an SSL parameters at HTTPS. In this way, the automatic hostname verification happens just like the HTTPS connection. So next part, we have Sazzadur to introduce a CryptoGuard, which is a detection tool.
Okay. So now I'll actually talk about the design philosophies and technical details of CryptoGuard. So CryptoGuard is a static analysis tool which is built on top of Suite's data flow analysis engine. And it takes source codes and APKs as inputs and does some pre-processing. And after that, it runs various rules to check cryptographic misuses. And for those rules, what it does is it uses different version of different slicing algorithm, forward and backward data flow, slicing algorithms based on forward and backward data flow analysis. And the specialty of these algorithms are they're specially customized by leveraging the insights from different programming idioms and language restrictions. And after that, after finishing the analysis, it actually produces the report. So precise detection of cryptographic misuse is actually a hard problem. And CryptoLint is one of the initial efforts that actually explored this problem. And since then, this problem got lots of attention from both industry and the academia. And CrySL is the state-of-the-art solution. But however, to be practical, we need to be have little little or as the false positives and false negatives need to be as low as possible. So most of the state-of-the-art tools tends to either producing more false positive or more false negatives. And CryptoGuard is the first solution to reach these practical criteria. So next, I'll talk about the different challenges that we faced during building this static analysis tool. So like any other static analysis tool, the main challenge we face is the trade-off among false positive, false negatives, and scalability. So to avoid high scalability, we actually avoid expensive path-sensitive analysis. So the next question is, how do we actually handle false positives? So in this slide, I will try to give you some idea about how we reduce false positive, or what are the insight behind. So first, let's assume that we want to find hard-coded keys from this code snippet. And now if we run backward data flow analysis from the program point new secret key spec, then we can find that default key is actually a hard-coded key. So now if we assume that the method bodies of some orthogonal invocations are missing during the analysis, like the key.getBytes or context.getProperty, then what will happen is this analysis will also report some other constants, hard-coded constants like passkey, pass.key, and UTF-8. And you can see that these doesn't actually impact the secrecy of the key. Thus, these are considered false positives. And other constants like data structure, bookkeeping variables can also contribute to the problem. So to reduce false positive, we use the insights from the Java programming language and also the idioms of common programming idioms. So for example, let's assume that the implementation for this method get bytes is not available during analysis. So in this line, the virtual invoke is used to invoke the virtual methods on the object key. And here UTF-8 is used to access that UTF-8 is actually indicating the state of the key material that we want to access. So we can actually see that these type of state indicator variables doesn't actually impact the secrecy of the key. So we can ignore these arguments of different virtual invoke functions. The same thing is true for various resource identifiers. So in this statement, we are using pass.key to access the or to restore or identify a resource from a key store or from a map or that of any data structure or any resources that lies in the memory. So again, here pass.key doesn't actually affect the secrecy of the key, and we can actually ignore that. The same thing happens for other resource identifiers too. So based on these observations, we created 5 heuristics or refinement insights to customize our data flow analysis algorithm. And we evaluated our CryptoGuard on around 46 real-world Apache projects and more than 6,000 Android apps. And our analysis shows that it actually helps us to reduce around 76% false alerts in Apache and around 80% of the alerts in Android. So this So this is the result of our manual analysis of Apache alerts. So we observed that around more than 1295 alerts, and our manual analysis confirms that there are only 18 false positives, which indicates the rate of 1.39%. So another challenge is so now we have scalable algorithms, data flow analysis algorithms, and we know how to reduce false positives to improve the performance. But for the scalability, these are not enough. For example, the code we analyzed from Apache, one of the projects, Apache Hadoop, has more than 2 million lines of code, and the average lines of code were 4.2K. So to analyze or to have scalability of for analyzing these kind of projects, we need more design insights of how can we reduce the runtime overhead. So the main insight behind to overcome this challenge and optimize the performance is there are in large scale projects, large code bases, the codes are organized in modularized sub projects so that different modules or different sub projects can be reused by other software components. So here is a sub project dependency graph of Apache Ranger, and we can so during our analysis we can see that the only Apache Ranger plugins commons have some cryptographic API uses, and security admin sub project and plugins key sub project of the one plugins KMS are the sub project that relies these are the sub projects that rely on these Ranger plugin commons. So that means only these sub-project have some potential to have cryptographic misuse. Since none of the other projects have any cryptographic API use, or they depend on any other sub-project that has any sort of cryptographic API misuse. So this means that all the other we can actually ignore all the other sub-projects like Ranger util, Ranger plugins, audit, order KMS, things like that. And also the root sub-project. We call one sub-project as root sub-project if no sub-projects are dependent on this one. And the independent or root sub-projects can be also analyzed in parallel. So CryptoGuard doesn't only use backward data flow analysis, and for some of the other rules, it also uses forward data flow analysis. And one of the rule is to find insecure uses of SSL sockets that ER demonstrated. And for some other rules, we actually need multiple analysis. So for example, to detect the insecure usage of RSA key, first we have to identify whether an RSA algorithm is being used, and we also have to identify whether the key pair generator of the RSA key pair algorithm is initialized to find out whether the key pair generator is initialized with the right key. We have to run another round of analysis, that is backward data flow analysis or backward slicing. So to detect one cryptographic misuse, the use of multiple round of analysis is only possible because of the scalability of our algorithm or the lightweightness. And our analysis actually discovered lots of cryptographic misuses in top tier Apache projects, including Apache Spark, Apache Opbees, Apache Ranger. And these projects are being used by millions of users business across the world. So here is a code snippet in Apache, and I want to highlight the insecure portions of from these code snippets. And it has at least 3 cryptographic uses, and that's why I call it a zoo of cryptographic misuse. So first, code is used to initialize the this code is used to initialize the password-based encryption, the key for password-based encryption. So the first problem is it generates password. It generates salt from the password itself. So here you can see that when the password is as an argument and it's creating, it's copying the size of the salt into the salt variable, and that salt is being used as the salt for PB-based, password-based encryption. So it's nullifying the use of salt on the first place. So the main reason why we use is the unpredictability of the salt makes it indistinguishable even if 2 passwords are identical. But if we have deterministic salts, the security guarantee is gone. And we can also see that it uses weak MD5 hashing, well, just those salt or salt bytes. So since MD5 is broken, someone can actually, so this salt has the potential to give up the password itself. And also the number of iteration is used as the length of the password. And that means if the password is not of 1000 characters, then this the length parameter is also insecure. And for Android apps, our analysis actually new security insights. So we see that around 96% of the issues comes from new libraries. And most of the time, they are not even in the main application. So next, I'll hand over to Sharmin. Sharmin will talk about some of the APIs that we designed to detect different sort of to evaluate the performance of different cryptographic misuse detection tools.
I'm going to talk about Crypto API benchmark. Okay, so we built Crypto API benchmark, which is based on Java cryptographic API misuses. So mainly it contains about 171 unit test cases with 16 different cryptographic rules. So there were three major motivations for developing this Crypto API bench. The first one was we want to improve the, we want the tools to get better performance by improving their tools using the benchmark. And then we can compare different existing tools and find out their relative performance, their coverage, and let developers know that which tools is suitable for them to use. And the third motivation was we want to educate the novice developers who want to know about the cryptographic vulnerabilities, as the cryptographic as the benchmark contains the secure codes and insecure codes. So our benchmark is actually open sourced, and here is the there is the GitHub link here. So there is inside there's 16 folders representing the 16 rules, and you can see the 171 unit test cases inside these folders. And also there is an Excel file inside the GitHub where which files contains which vulnerability in which method and which lines these are. There are detailed information about the file exists in the benchmark. So here is the Crypto API bench structure. We have 40 basic cases and 131 advanced cases. The basic ones is very straightforward, and it has like a very small case, just one procedure, and the source of vulnerability exists within the like originate within the same procedure. And in the advanced cases, they have we have interprocedural, field sensitive, combined cases, path sensitive cases, multiple class, and some miscellaneous map interface cases. We will see just a couple of examples on these advanced cases. So here is an example of interprocedural case. So what happens here in this case is that you can see this line, the PB parameter spec. This actually specifies a set of parameters, salt and iteration count. It defines these two parameters for password-based encryption. And to be secure, this iteration count value should be greater than 1000. And if the count value is less than 1000, then it's considered insecure. So let's track that what's the value of this count, the iteration count value. So if you see the main method, this count value is 20, and then it's actually passing to this another procedure and use this count value here. So what's the purpose of having this unit test case? So this case actually checks the tool's ability to find out like whether it can identify the count value coming from a different procedure. Next, we have the path-sensitive advanced case example. So this is also the password-based encryption example, but here instead of having like different procedures, we have the conditional statement here. So we can see that first this iteration count value was 5, which is insecure. Now, based on this choice value, the count can be 5, which is insecure, or the count can be changed to 1050, which will become secure. So this unit test case, it identifies whether a tool can determine the count value from conditional statement. Okay. So now, when we have the Crypto API bench, we were grateful that there are several cryptographic vulnerability detection tools. We evaluate the spot bugs, CryptoGuard, CryptoGuard, and Scalability for the comparison. As I have already said that in Crypto API bench there were 16 rules, but we found that among them 6 common rules was covered by 4 of these tools. So to be fair, we compare these tools only based on these 6 common rules. So this is the evaluation results for the basic cases, and the second table is evaluation result for the advanced cases. If we see the basic case result, we see that the spot bugs, CryptoGuard, and Scalability, they have a similar result and gives better performance than CryptoGuard, because CryptoGuard have more false positive and false negative values than the other tools. And for the advanced cases, we see that the spot bugs, the recall and precision value is 0. It's because that spot bugs is not designed to capture any advanced cases. We find another interesting point that none of these tools actually handle the path-sensitive cases. And another thing I have to mention that this result is based on around March 2019, around that time's result, because we reported this in our Crypto API bench SecDev paper. But since then, an amazing thing is that CryptoGuard is evolving, and they are actually getting evolving, and they incorporate Crypto API bench as their test suite, and they are getting improved results. So, and if you want to more about the Crypto API bench or the insecure secure cases or the tools coverage or performance, you can welcome to see the paper and also the GitHub page. So in the next, we'll show the perfect results.
Next, I will briefly introduce my experience about how to reuse the insights of CryptoGuard in other vulnerability detection tools to achieve the high precision. And first, I want to introduce another tool called Parfait, an Oracle Parfait. It is a scalable bug scanner, which is developed and maintained by Oracle Labs, and it covers various types of vulnerabilities. For example, like the defects from the CWE top 25 vulnerability list. And currently, Parfait also covers a module called Parfait Crypto Scanner, which integrates the precise and scalable cryptographic API misuse detection. And this work is done by me as I was an internship working in the Oracle Labs Australia. And these are the collaborators. And we currently, we have a paper in the archive, and welcome to check that. And Parfait actually has some special designs to promote the scalability. And in order to reuse the refinement program slicing insights and heuristics from the CryptoGuard, we have to tailor the CryptoGuard algorithm under the support and the frameworks of Parfait. Here I just introduce a major difference. Like this is a layered framework of Parfait. Parfait actually it's optimized all the analysis in order from quickest to slowest to guarantee the scalability. And in this way, like the more vulnerabilities can be reported with a lower time overhead. And specifically, for example, to perform our backward interprocedure program slicing, and the analysis starts from the slicing criterion in method A, and after reaching the entry point of method A, we need to like jump to its caller, method D, and if the analysis has not been terminated, we need to even jump to its caller's caller, method F. However, in Parfait's framework, all of these things are broken down into different layers, like the method A, the analysis happens in method A, and the other analysis are all scheduled in layer 1. And if the analysis has not terminated, we just perform other analysis in the same layer. And after that, we go into the next layer 2 for its caller. In this way, like all the vulnerability requiring the lowest time overhead could be reported quickly. And we also test our Parfait-based crypto scanner in the crypto API bench to test its precision. And we can find that it has a really excellent recall and very few false negatives here. And for the precision, all the false positives come from the path sensitivity cases. So the precision, excluding the path sensitivity cases for other cases, are all very good. And another important issue for another important feature for our Parfait is the scalability, because we expect it to be run for some large code bases. So we tested many internal large code bases of Oracle, and the precision is verified manually. And we also found that the precision is really high. And we also record the runtime performance of these code bases and the line of code. We found that most of the project can be finished within 10 minutes. And also, even with some of them has millions of code, the runtime is still pretty good and less than 10 minutes. And next, we will have Myers to introduce some demo about how to use our CryptoGuard.
And next, I'll present how to use CryptoGuard using a live demo. So for the setup that I'll be using two different major technologies. The first one called Binder. And you can think of Binder as a service that creates a virtual environment for you. And I'll also be using a Jupyter notebook, and you can also think about that as a live web browser-based IDE. And for our specific setup, we need to use the iJava Jupyter notebook. And for this demo, You can follow along at any time after this video. Once you open the specific website, my binder or binder will actually retrieve all of the information from GitHub and create its own virtual environment. And from that, the virtual environment will automatically start the Jupyter Notebook, so you can easily walk through and go through each step of the notebook itself. So as you can see here, I have the video of the demo, and again, feel free to follow along or go back to the actual notebook itself at this hyperlink. To start off with, I've already pre-ran all of the cells or all of the code logic, since the tests do take some time. And of course, at the top of every program, especially with the Jupyter Notebooks, you need to import all the necessary libraries and dependencies. And specifically for this case, for this command, this allows us to load a CryptoGuard jar, and that's hosted within the same environment of the virtual environment itself. And as you can see, there's still a lot of imported dependencies for this demo. And currently, this cell shows us what version of CryptoGuard we're demoing. And currently, we're looking at version 04.05.01. If we go a little further, since CryptoGuard requires Java version 8, and this notebook requires a different version of Java, this cell allows us to pass the correct path of Java 8 to CryptoGuard and allow us to continue through with this demo. And if we go to the next cell, all of these methods and all of these paths are created and set up to help support all of the test methods. And as you can see, we have a short method to show approximately how long each test took. And for the first test section, we have Android APKs. And again, this cell, which is all Java code, it sets up the paths to the files that are to be written out and the source. So if we look here, this first test is directly taken out of the live CryptoGuard test suite and directly put into here. And to go more specifically into the direct usage of CryptoGuard, we have a string that controls all of the arguments passed in. And throughout this test and these similar test cases, all of these are passed in exactly how they would be used from the command line. And I'll quickly go over each argument really quick. So the first argument specifies that we're looking at an Android APK. The second argument specifies the specific path to the APK. Third argument specifies the format that we'll be printing or writing out the contents. And in this case, we'll be using legacy format. The next two arguments specify the paths to the Android SDK and the Java 8 environment as well. And I'll skip over the next argument, since this argument should only be used for testing purposes. And the last argument is specifying the file that CryptoGuard will actually write the results out to. If we go a little bit further, you can see all of these arguments right before they're entered into CryptoGuard, how they actually look. And this can be used as a frame of reference to use CryptoGuard directly on the command line. So since this scan is already completed, let me skip ahead to the results. And there we go. As we can see, CryptoGuard successfully scanned the appdebug.apk, and as stated earlier, MD5 is likely an insecure hash that was successfully picked up by CryptoGuard in the following package. And if we scroll down further, we can see more of the rules broken, such as constant code or untrusted PRNG. And if we go, and the test took approximately 35 seconds. So if we go to the next test, still scanning the same source file, we instead change the file out of the format to use a specific XML format. And this was previously requested for CryptoGuard. And throughout the redesign of CryptoGuard, we're able to successfully print out the same results to the XML format. And this is the same contents of the scan above, since it's scanning the same APK file. And if we go to the next test, you'll see we're not specifying any format out, as we set JSON as the default format out. And if we scroll to the bottom, you can see all of similar attributes are set into the JSON output. And if we quickly go to, I believe, this last APK test, we're specifying to use a CSV type format out, which, like the previous tests before, writes out the examples in the specific usable CSV format. And next we'll lightly go over how CryptoGuard can scan Java class files. And like the APK test set above it, this cell sets up all the necessary paths for scanning Java class files. And to note, specifically in this test, we're allowed to put an invalid path for the Android APK, since that isn't used in scanning Java class files. And below that, we have two specific arguments, notably stream and pretty. Pretty formats the output that's printed out or written out by CryptoGuard. And we'll see it down below in the results. And stream, most notably, allows CryptoGuard to write out the test results to the file instead of gathering all of the results and writing all of the file at the end of the execution. And this helps alleviate any kind of memory strain on the JVM. And so if we quickly go check the results, we'll see that the output is still in XML format, but it's properly formatted this time and more human readable than the previous output. And last but not least, for Java classes, we'll also look into how CryptoGuard can also write out the input to a YAML type format. Quickly scroll to test results. All of the results are printed out in a YAML-based format for even more usability if CryptoGuard is used as a dependency or library. Now, following that, we'll go over how CryptoGuard can scan a jar file. And like with the tests above, this test setup is similar. And instead, we pass in the Java jar file, And the only extra argument passed in is a time measure Boolean, which allows CryptoGuard to quickly print out approximately how long the test and the scan took from its side. And while I'm still waiting to scroll down, previously in all the tests we check if the operating system is a Linux type, and that's solely due to the fact that CryptoGuard can only be used, currently only be used on a Linux system. And as you can tell from the printout, it's commented to allow the file out to still be a valid XML format. And it took approximately 8 seconds from CryptoGuard's side. And to allow CryptoGuard to be used in more cases than on the command line as showed here, we also started hooking CryptoGuard into Java build tools. And these plugins for the build tools only help to pass the information from the project to CryptoGuard, as it only retrieves relevant information such as the source code and dependencies and passes that to CryptoGuard to scan all of the files. And then after this happens, all of the information is returned in a proper file format to the user. And since this is a Java-based language and project, we're aiming to look into Maven and Gradle for the top 2 build tools we use. And of course, the plugins are aptly named Maven Guard for Maven and Gradle Guard for Gradle. And since these tools are still under active development, they each currently only support 3 different tasks. And these tasks are version, which prints the current version of CryptoGuard in the plugin, preview files, which allows the user to see which files are picked up from the plugin to allow CryptoGuard to scan, and scan files, which of course sends all the files and information to CryptoGuard to scan. And like I said, all 3, CryptoGuard and each plugin, are still under active development. We would welcome any pull requests or any insights into each of the projects, as can be shown from these links here. So I would like to now pass it off to Dr. Sazzadur Rahaman so he can dive more into Spring security misconfiguration issues.
So I want to emphasize more on one point. So we have multiple types of our input-output formats for CryptoGuard. So this is basically done so that CryptoGuard can be easily integrated with any sort of platform or static analysis platform that you have in your development environment or even in production environment. So if you think you can leverage our tool to help secure code in your organization or personally, then feel free to reach us out. So next, what I am going to talk about is application framework configuration misuses. So not only libraries are being misused, but also the application frameworks are also, the configuration especially for different application frameworks are also being heavily misused by the community. And there is a talk coming up in the main conference and will be presented by Mazhar. So I'll not spoil his talk in this tutorial. Just I will give you a teaser like what sort of security anti-patterns we found during our exploration. So one thing in his talk, he will actually talk about how different lifelong valid access tokens can affect security of the Spring applications, and how developers manually disable protections that are provided by default in Spring security, and some other security anti-patterns. And if you have any questions, feel free to reach us out. And finally, thank you for watching this.
All right, thanks everyone for the wonderful tutorial, different components. I just want to quickly add a couple of things. First, Java 8, it's the limitation right now is because of suit does not support Java 9 and above. And so again, community contribution. Parfait does not use a CryptoGuard directly because they have their own framework, as Jan explained, and then some of their analysis is built on top of LVM, I believe. And so, so that explains. Need to do a lot of did a lot of work during her internship to fit CryptoGuard detection in Parfait. Anything else to add before we end the recording? All right. And so, bye everyone.